Look up, not at a screen, not at a ceiling. Imagine looking up through all of it, through the roof, through the atmosphere, through the thin blue skin of air that keeps you alive, through the dark between the stars, and trying, genuinely trying, to understand what is out there. You already know it is large. You have been told this your entire life. The universe is vast, they say. The universe is incomprehensibly big. And you nod, because what else do you do with a fact like that? You file it somewhere in the back of your mind next to other things that are technically true but impossible to feel. You move on with your day. Tonight, we are going to try something different. We are not going to list numbers at you and hope something sticks. We are not going to say 100 billion galaxies and expect that to land. We know it does not land. We know that human brains, built over hundreds of thousands of years to navigate a world measured in feet and miles and days, were never designed to process distances measured in billions of light years. The brain hears those numbers and nods politely and files them away and continues worrying about smaller things. What we are going to do instead is take you somewhere. We are going to start with something you know, something you can picture, something with a shape you have seen your whole life. And then, step by step, we are going to pull back. We are going to keep pulling back, further and further, until the things you know are gone, not just distant, but invisible, absorbed into the background noise of something so much larger that your starting point is statistically indistinguishable from nothing. We begin with planets, things with names: Jupiter, Saturn, the ringed one, the red one. You know these, they feel real. By the end of this journey, we will be looking at a structure so large that the entire observable universe, everything humanity has ever seen, every galaxy ever photographed, every star ever named, is threaded through it like a single fiber in a piece of cloth. The universe has a shape, not a metaphorical shape, a literal, physical, measurable architecture that emerged over 13.8 billion years, from almost nothing, built by nothing more extraordinary than gravity and time. It looks like a web, an enormous, three-dimensional web of dark matter and gas and ancient light, stretching from one end of everything we can see to the other. You are inside this web, not watching it, not studying it from a safe distance. You are a small thing on a small planet in a small system in a minor arm of one galaxy in one small cluster on the edge of one supercluster in one filament of this web. The only way to understand how small you are is to understand how large everything else is. So, let's begin close to home. Earth has a diameter of roughly 7,900 miles. That is the number. And if you have spent your entire life on this planet, if every mountain you have ever climbed, every ocean you have flown over, every road trip that felt like it would never end was contained within that single number, then 7,900 miles feels enormous. It is the biggest thing you know from the inside. It is not enormous. Jupiter, the largest planet in our solar system, has a diameter of approximately 86,000 miles. It is 11 times wider than Earth. You could line up 11 Earths across Jupiter's face, and they would just barely fit. You could fit 1,300 Earths inside Jupiter's volume with space left over. Jupiter is so large that if you tried to place it on Earth's surface, it would dwarf the planet entirely. The Great Red Spot, a storm that has been raging in Jupiter's atmosphere for at least 350 years, is itself wider than Earth. Jupiter is so massive that it slightly distorts the orbital behavior of everything around it. The gravitational relationship between Jupiter and the Sun is unusual enough that both objects technically orbit a shared center of gravity, a point called a barycenter, that sits just outside the surface of the Sun. Jupiter does not simply orbit the Sun the way smaller planets do. They are more like a pair, in slow mutual orbit, with everything else arranged around them. And Jupiter, for all of this, is a modest planet by the standards of the universe. In the last 3 decades, astronomers have discovered thousands of planets orbiting other stars, worlds we call exoplanets. Among them, a gas giant significantly larger than Jupiter. HAT P32b has a radius approximately 2 times that of Jupiter. Roxy's 42Bb has a mass estimated at around 9 times Jupiter's. WASP 17b is nearly twice Jupiter's radius, but only about half its mass. An inflated balloon of a world, puffed up by the radiation of its host star, a planet so strange that it orbits its star backwards in the direction opposite to the star's own rotation. Then there are the rogues. Rogue planets are worlds with no star. Not because their star died, though some may have formed that way, but because they were ejected from their original solar systems early in their formation. Gravitational interactions between giant planets during the chaotic early period of a solar system's life can fling one of them outward at escape velocity, sending it tumbling into the interstellar dark. Once ejected, there is nothing to slow it down and nothing to pull it back. It drifts forever. Rogue planets exist in permanent night. No sunrise, no seasons, no tides, no warming light from any direction. Just the cold of interstellar space, the faint background heat of the universe itself, and whatever residual warmth their internal radioactive decay can generate. Current estimates suggest rogue planets may outnumber stars. For every star visible in the night sky, there may be several dark, silent worlds drifting unseen between them. The galaxy may be full of places, worlds of rock or gas or ice that no light has ever touched for billions of years, that no being will ever walk across, that exist in a darkness and silence so complete that our language has no adequate word for it. Even the largest of these planets, however, is at the next scale of this journey invisible. Not just small invisible, a speck in a search image, a rounding error in a catalogue. There is something worth sitting with here before we move on. Jupiter, a planet so large it contains 1,300 Earths, orbits the Sun at a distance of almost 500 million miles. It takes light 43 minutes to travel from the Sun to Jupiter. The entire volume of Jupiter, that 1,300 Earth container, is invisible to the naked eye from the next star over. From Alpha Centauri, 4 light-years away, Jupiter would be undetectable without specialized instruments. This is before we have even started. Jupiter, the giant, is already gone before the journey has properly begun. The Sun has a diameter of approximately 864,000 miles. That is more than 109 times the diameter of Earth. If the Sun were hollow and you could fill it with Earths, you would need 1.3 million of them. If you could drive a car at highway speed from one side of the Sun to the other, the journey would take just under 200 years. If you could walk it, assuming the surface was somehow cool and solid enough to walk on, it would take several thousand years of continuous walking to circle the equator once. The Sun is a small star. It sits comfortably in the middle of the stellar mass distribution, a yellow dwarf, classification G2V, unremarkable in its size, its brightness, its temperature, its age. There is nothing about the Sun that distinguishes it from the vast majority of stars in the galaxy. It is ordinary. It is medium. The most common stars in the universe are red dwarfs, cool, dim, small objects with masses between roughly 8% and 50% of the Sun's mass. They burn their nuclear fuel so slowly, so carefully, that they can survive for trillions of years. The universe is currently only 13.8 billion years old. Every red dwarf that has ever formed in the history of the universe, every single one across all galaxies since the first stars were born, is still burning. Red dwarfs do not go out. Not on timescales that mean anything to us. On the other end of the scale entirely are the hypergiants. Betelgeuse, the red supergiant in the upper left shoulder of Orion, is one of the most famous large stars in the sky. It has a radius somewhere between 700 and 1,000 times that of the Sun. Its size is difficult to pin down, precisely because it is not spherical, because it pulses, and because it has large convective cells on its surface that cause irregular variations in its apparent diameter. If you placed Betelgeuse where the Sun is, its surface would extend somewhere past the orbit of Mars. On its largest days, its outer atmosphere might brush the orbit of Jupiter. Betelgeuse is expected to end its life in a supernova at some point within the next 100,000 years. When it does, it will briefly outshine the full moon in Earth's night sky, visible in daylight. Astronomers will see it coming. They are already watching. But Betelgeuse is not close to the largest star we know. Stephenson 2-18 is a red hypergiant located approximately 19,500 light-years from Earth in the constellation Scutum. It sits within a young star cluster called Stephenson 2. Its radius is estimated at approximately 2,150 times that of the Sun. 2,150 solar radii. If you place Stephenson 2-18 where the Sun is, its surface would extend well past the orbit of Saturn, past Saturn, which is 900 million miles from the Sun. The distance from the Sun to Saturn, which takes light 79 minutes to cross, would be entirely inside the star. The surface of the star would be almost 2 billion miles from where the Sun currently sits. It would take light more than 8 hours to travel from one side of Stephenson 2-18 to the other. And yet, stars have a physical size limit. As a star grows more massive, the radiation pressure produced by its nuclear fusion pushes outward with increasing force against its own gravity. At a certain mass, somewhere around 150 to 300 times the mass of the Sun, this radiation pressure becomes so powerful that it overwhelms the star's gravitational binding. The outer layers are blasted away. The star cannot hold itself together. Nature has a ceiling. What happens when stars die is worth a brief pause, because the remnants they leave behind represent an entirely different kind of extreme. When a star like the Sun exhausts its fuel, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, Earth-sized cinder containing roughly half the Sun's mass, packed into a sphere no larger than our planet. A teaspoon of white dwarf material would weigh approximately 5 tons on Earth. More massive stars end more violently. In a supernova explosion, the core of a dying star can collapse in less than a second, a freefall so rapid that the outer layers of the star, still moving inward, rebound off the dense core and explode outward at a significant fraction of the speed of light. What remains is a neutron star, an object roughly 12 miles across, containing the mass of the Sun, with gravity so intense that a marshmallow dropped from 1 meter above its surface would hit with the force of an atomic bomb. A neutron star is not made of atoms. The electrons and protons have been crushed together into neutrons, and the neutrons themselves are packed so tightly that the entire object is essentially a single atomic nucleus 12 miles in diameter. Stevenson 2-18. The neutron stars, the white dwarfs. The full range of stellar existence, from barely a star red dwarfs to hypergiants large enough to swallow Saturn's orbit. All of it contained within the galaxy's disk. All of it context for what comes next. Between the stars, space is not empty. It is threaded with gas and dust, vast clouds of hydrogen and helium and heavier elements, the raw material of everything. These clouds are called nebulae. They are among the most beautiful and most violent structures in the galaxy, and some of them are large in a way that starts to stretch the word. The Orion Nebula is the closest large star-forming region to Earth, approximately 1,300 light-years away. On a clear, dark night, it is visible to the naked eye as a faint smudge in the Sword of Orion, one of the only clouds of gas you can see without a telescope. In photographs, it glows in pinks and blues and golds, ionized gas lit from within by young, hot stars forming at its core. Its total diameter is approximately 24 light-years. Light takes 24 years to cross it. The Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible from the southern hemisphere, is approximately 1,000 light-years across, 40 times larger than the Orion Nebula. If the Tarantula Nebula sat where the Orion Nebula sits, it would span roughly a quarter of the entire night sky. It would be bright enough to cast visible shadows on Earth at night. It contains the most luminous star systems known to exist, young, massive, burning with an intensity that makes our sun look like a candle. Nebulae are not passive scenery. They are stellar nurseries, places where gravity is winning its slow war against the outward pressure of gas, where collapsing regions are growing dense enough, hot enough for nuclear fusion to ignite. The pillars of creation, the towering columns of gas in the Eagle Nebula, photographed by Hubble in 1995 and in extraordinary detail by the James Webb Space Telescope in 2022, are 5 light-years tall. Stars are forming inside them right now. We cannot see the newly forming stars yet because they are buried deep in the dust. But in a few 100,000 years, when the radiation from those young stars erodes the pillars away, they will be revealed. The process of star formation is slow on a scale that is difficult to appreciate. A molecular cloud, a cold, dense pocket of a nebula, may take millions of years to collapse into a protostar. That protostar then spends millions more years accumulating mass, blasting away its surrounding cocoon of dust with its radiation and stellar winds, before finally emerging as a young star and joining the galaxy's general population. The pillars of creation will be gone in 3 million years, eroded by the radiation of the cluster forming inside them. That 3 million years, an interval so vast that modern Homo sapiens have only existed for about 1/3 of it, is, on the timescale of a star's life, barely a moment. Every star that has ever existed was born inside a nebula. The Sun was born in 4.5 billion years ago. The nebula it formed in has long since dispersed, but its material, the gas and dust that did not become the Sun and the planets, is still out there, mixed back into the interstellar medium, waiting to form something else. The atoms in your body passed through at least one stellar nursery before they became you. Possibly several. Stars rarely form alone. They form in groups, sometimes dozens, sometimes millions, from the same collapsing cloud of gas. The siblings born together in the same stellar nursery are called a star cluster. Young star clusters, open clusters, are loose, scattered collections of a few hundred to a few thousand stars, all roughly the same age. gradually drifting apart as the galaxy's differential rotation slowly pulls them in different directions. The Pleiades, visible on a clear night as a tight grouping of blue-white stars in Taurus, is a young open cluster about 440 light-years away. The stars in the Pleiades are only about 100 million years old teenagers by stellar standards. In another 250 million years, the cluster will have dispersed entirely, its stars scattered through the galaxy. Globular clusters are something different entirely. A globular cluster is a dense, spherical collection of anywhere from 10,000 to several million stars, held together by their mutual gravity in a sphere typically between a few tens and a few hundred light-years across. The density at their cores is extraordinary. In the center of a typical globular cluster, stars are separated by distances measured not in light-years but in light-weeks, a tiny fraction of the distance between the Sun and its nearest neighbors. If our solar system sat at the center of a rich globular cluster, the night sky would be spectacular. Thousands of stars bright enough to cast shadows, a blaze of light in every direction, the sky never truly dark. Globular clusters are ancient. The oldest of them formed when the universe was less than 1 billion years old, and they have been orbiting their host galaxies in highly elliptical looping paths ever since. The Milky Way has approximately 150 known globular clusters. Omega Centauri, the largest, contains roughly 10 million stars in a sphere about 150 light-years wide. It orbits the Milky Way on a path that carries it far above and below the galactic plane, completing each orbit over hundreds of millions of years. Think about what that means in practice. Omega Centauri has completed perhaps 40 or 50 orbits of the Milky Way since it formed. During that time, every major event in the history of life on Earth has occurred. The Cambrian explosion, the age of dinosaurs, the extinction, the rise of mammals, the appearance of humans, the entirety of human civilization recorded history, all of it fits inside a single fraction of a single orbit of this ancient cluster around our galaxy. The cluster was already old before the first fish crawled onto land. It will still be orbiting long after the Sun has died. Some astronomers believe that Omega Centauri is not a true globular cluster at all. Its size, its multiple stellar populations of different ages, and the presence of what may be a mid-mass black hole at its center suggest it might be the stripped core of a small galaxy, a dwarf galaxy that fell into the Milky Way billions of years ago, its outer stars pulled away by tidal forces, leaving only the dense, ancient heart behind. The Milky Way has been eating smaller galaxies its entire life. The Milky Way is a barred spiral galaxy, a flat rotating disk of stars, gas, and dust, with a central bar of older stars and several curved spiral arms extending outward. Its disk is approximately 100,000 light-years across, though the true outer boundary of the galaxy, including its stellar halo, and the full extent of its dark matter halo, reaches much further. The total diameter, including the halo, is estimated at between 150,000 and 200,000 light-years. It contains between 100 billion and 400 billion stars. The range is uncertain because counting stars in the galaxy is like counting trees in a dense forest. From the inside you can sample, you can estimate, but a precise census is beyond our current reach. At the center of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass approximately 4 million times that of the Sun. We have imaged it in 2022. The Event Horizon Telescope collaboration released the first direct image of our galaxy's central black hole, a glowing ring of light around a dark shadow 2,500 light-years away. It is, by the standards of supermassive black holes, relatively small and relatively quiet. It is not currently consuming large amounts of material. It is not currently producing jets. It sits there, at the center of everything, patient and dark. The Milky Way rotates. Our solar system, located approximately 26,000 light-years from the galactic center in a minor spiral arm called the Orion Arm, travels around the galactic center at approximately 500,000 miles per hour. One complete orbit takes approximately 225 million years. The last time the solar system completed a full orbit and returned to roughly this position, the Triassic period was just beginning on Earth. Dinosaurs had not yet evolved. We have never seen our own galaxy from the outside. Every image labeled the Milky Way in popular science is either a photograph of another spiral galaxy used as an illustration, or an artistic reconstruction assembled from data, or a composite of what we can observe from inside combined with our best models of what the outside should look like. There is no vantage point from which a human-built instrument has ever looked back at the whole Milky Way and photographed it. There is an additional structure to the Milky Way that does not show up in most artist impressions: its dark matter halo, surrounding the visible disk of stars and gas surrounding it in every direction, extending far beyond the last stars at the galaxy's edge, is a vast spherical halo of dark matter. This halo is much larger than the visible galaxy. Where the stellar disk extends perhaps 100,000 light-years, the dark matter halo extends perhaps 600,000 light-years or more in every direction. It contains, by mass, far more material than all the stars and gas combined. The dark matter halo is the true body of the Milky Way. The stars are just a thin, luminous disk inside it, the visible fraction of a much larger, invisible object. We live inside something we cannot see. We are part of a structure we can only imagine. And what we have imagined, based on decades of painstaking measurements and observations and modeling, is something extraordinary. But the Milky Way is not where the story ends. It is barely where the story begins. The Milky Way is not alone. Gravity does not allow it to be. Surrounding the Milky Way, gravitationally bound to it in a loose collection called the local group, are approximately 54 known galaxies spread across a region roughly 10 million light-years in diameter. Most of these are dwarf galaxies, small, irregular, containing a few billion stars at most. The large and small Magellanic Clouds, visible from Earth's southern hemisphere as bright patches in the night sky, are the two largest satellite galaxies of the Milky Way. They are currently being gravitationally disrupted by the Milky Way's tidal forces, their stars slowly stripped away, their shapes distorted, their eventual fate to be absorbed entirely. The Milky Way has done this before. The remnants of several ancient dwarf galaxies can still be traced in streams of stars orbiting the Milky Way at great distances, the debris of mergers that occurred billions of years ago. The most significant neighbor is Andromeda. The Andromeda Galaxy Messier 31 is the largest galaxy in the local group, containing somewhere between 1 trillion and 2 trillion stars. It sits approximately 2.5 million light-years from Earth. On a clear, very dark night, far from city lights, it is visible to the naked eye as a faint smudge, about 3 times the angular width of the full moon, the most distant object a human being can see without optical aid. That light left Andromeda 2.5 million years ago, when our ancestors were early Homo on the African savanna. Andromeda is moving toward us. It is approaching the Milky Way at approximately 110 kilometers per second, roughly 68 miles per second. In approximately 4.5 billion years, Andromeda and the Milky Way will begin to collide. It will not be a sudden, violent impact. It will be a slow, gravitational dance that unfolds over hundreds of millions of years. The two galaxies will approach each other, interpenetrate, swing past, loop back, and eventually, over the course of perhaps 2 billion years, merge into a single, much larger galaxy. Direct star-on-star collisions will be extraordinarily rare, because the space between stars is so vast that even two galaxies passing through each other is, at the level of individual stars, mostly empty space, moving through empty space. But the gravitational disruption will be total. Spiral arms will be shredded. Stars will be thrown onto new orbits. The night sky 4 billion years from now will be dominated by the expanding light of Andromeda and then by the chaos of the merger itself. Astronomers have already named the product Milkomeda. They have run the simulations many times. The outcome is not in doubt, only the details of individual stellar trajectories. Our solar system will probably survive, but where it ends up in the merged galaxy is uncertain. The Sun and its planets may find themselves in a completely different region of the new elliptical galaxy. Surrounded by stars that were once in Andromeda, the old familiar neighborhood of the Milky Way dissolved beyond recognition. Everything we think of as our cosmic home, our address in the universe, will have been erased. The Milky Way is a large galaxy, not the largest, not the smallest, but toward the upper range. Most galaxies are considerably smaller. The universe is full of dwarf galaxies. Small, irregular, faint systems with a few billion stars orbiting larger galaxies, slowly being consumed. But some galaxies are orders of magnitude larger than the Milky Way. Elliptical galaxies, ancient, red, diffuse, no longer forming new stars, are some of the most massive objects in the universe. They form when spiral galaxies collide and merge, their orderly rotation disrupted by the violence of the encounter, the stars finding new, random orbits that combine into a rough sphere or ellipsoid. Over billions of years, star formation shuts down, the hot blue young stars die off, and only the old red stars remain, giving elliptical galaxies their warm amber glow. IC 1101 is one of the largest known galaxies. A supergiant elliptical galaxy at the center of a cluster called Abell 2029, located approximately 1 billion light-years from Earth. Modern measurements place its diameter at roughly 500,000 light-years across its brightest regions, with diffuse outer material extending somewhat further. That is still roughly 5 times the diameter of the Milky Way's disk. It formed through repeated mergers over billions of years, cannibalizing smaller galaxies one after another. Its stars are spread across an enormous, diffuse volume with no clear edge, the accumulated debris of a long history of cosmic consumption. It contains an estimated 100 trillion stars. That is 100,000 billion stars. If you counted 1 star per second without stopping, pausing for nothing, it would take 3.2 million years to finish. In 2003 and 2004, astronomers pointed the Hubble Space Telescope at a carefully chosen patch of sky in the constellation Fornax. The patch was selected specifically for its apparent emptiness, very few bright foreground stars, no known bright objects to give the telescope an unobstructed window into the deep universe. The telescope stared at this patch for 11 consecutive days, collecting every photon it could. The resulting image, the Hubble Ultra Deep Field, revealed approximately 10,000 objects. Nearly all of them are galaxies. The patch of sky in that image is tiny. It covers approximately 1/13 millionth of the total sky. If you held a grain of sand at arm's length, it would cover approximately the same area of sky as the Hubble Ultra Deep Field. That grain of sand's worth of sky contains 10,000 galaxies, each one a collection of billions or hundreds of billions of stars, each one potentially surrounded by planets. Extrapolating across the entire sky and accounting for the fact that even the deepest Hubble images are still missing the very faintest galaxies, astronomers estimate the observable universe contains somewhere between 1 trillion and 2 trillion galaxies. The James Webb Space Telescope, with its superior infrared sensitivity, has been finding galaxies even further back in time and even more numerous than Hubble suggested, and some of them are far larger and far more evolved than they should be at their ages. Another puzzle that the universe has set us without yet providing the answer. 2 trillion galaxies, each one a universe unto itself. Most of the universe between galaxies is not matter, it is not gas, it is not dark matter, it is nothing. The average distance between galaxies in a typical part of the universe is several million light years. In that space, those millions of light years of void, there are no stars, no planets, no nebulae, no clusters, no cosmic rays of any significance. There is the intergalactic medium, a ghostly, ultra-thin plasma of ionized hydrogen and helium at temperatures of millions of degrees, but densities so low that a cubic meter of intergalactic space contains, on average, less than 1 atom. It is a vacuum more perfect than anything we can produce on Earth. Consider for a moment what it would mean to exist in that space. Not on a planet, not in a solar system, just in intergalactic space. The nearest star would be millions of light years away in every direction. The sky would contain no constellation patterns, no familiar stars, no Milky Way overhead, just the faint, distant smudges of galaxies, each one separated by distances so vast that a civilization without knowledge of cosmology might conclude the universe consisted of isolated islands with nothing in between. The silence and the dark of intergalactic space would be of a completeness that has no equivalent anywhere in ordinary human experience. The galaxies are not scattered randomly. They form a pattern. Something has organized them into a structure so large that individual galaxies are invisible within it. Galaxies do not usually exist in isolation. They exist in groups. Groups exist in clusters. And at each step up the hierarchy, the scale becomes something that requires a new kind of language to describe. A galaxy cluster is a collection of anywhere from dozens to several thousand galaxies, gravitationally bound into a single coherent object. They are the largest gravitationally bound structures in the universe. Below the scale of galaxy clusters, you can have individual objects, stars, planetary systems, galaxies that are held together by their own self-gravity. Above the scale of galaxy clusters, you have structures that are associated and in each other's gravitational influence, but are not truly bound. They will eventually be pulled apart by the expansion of the universe. The Virgo cluster is the nearest large galaxy cluster to our local group, sitting approximately 53 million light-years away. It contains roughly 1,300 galaxies, dominated by several giant elliptical galaxies at its core, spread across a region approximately 8 million light-years in diameter. At the heart of the Virgo cluster sits M87, a supergiant elliptical galaxy containing a supermassive black hole 6.5 billion times the mass of the Sun. This is the black hole, photographed by the Event Horizon Telescope collaboration in 2019. The first direct image of a black hole ever captured. The Perseus cluster, 240 million light-years away, is one of the most massive known galaxy clusters. It contains over 1,000 galaxies bound together by their mutual gravity and surrounded by an enormous halo of superheated gas, the intracluster medium glowing in X-rays at temperatures approaching 50 million degrees. The X-ray halo spans more than 1 million light-years. In 2003, astronomers analyzing X-ray observations of the Perseus cluster noticed something unusual: ripples in the hot gas, pressure waves propagating outward from the supermassive black hole at the cluster's center, driven by periodic jets of energy fired by the black hole into the surrounding medium. The ripples were sound waves, actual acoustic pressure waves traveling through the cluster's hot gas. Their frequency corresponded to approximately 57 octaves below middle C. A single wave in this sound took about 10 million years to complete its cycle. It is the deepest note ever detected in the universe, produced by a black hole and played through an instrument the size of a galaxy cluster. Galaxy clusters do not simply exist passively. They evolve. They consume smaller groups and subgroups. They strip gas from infalling galaxies, a process called ram pressure stripping, where the hot intracluster medium acts like a headwind on galaxies passing through the cluster, sweeping their gas away and shutting down their star formation. They bend light from distant objects behind them through gravitational lensing, distorting space sufficiently to act as enormous natural telescopes, allowing us to see objects even further away than the cluster itself. The Hubble Frontier Fields program deliberately targeted 6 massive galaxy clusters and used them as gravitational lenses to study objects far behind them. Clusters like Abell 2744 and Max J0416 bent and magnified the light of galaxies billions of light-years further away, revealing galaxies that would have been completely invisible without the cluster's lens effect. The most massive clusters act as gravitational machines of extraordinary power, reshaping the environment around them for hundreds of millions of light-years in every direction. Above galaxy clusters, the hierarchy continues. A supercluster is a region of space containing a collection of galaxy groups and clusters in a loose association. Most superclusters are not gravitationally bound. Unlike galaxy clusters, they will not survive indefinitely as coherent structures. The accelerating expansion of the universe will gradually pull their component clusters apart over billions of years, and what is today a recognizable supercluster will become, in the far future, a collection of isolated clusters drifting in expanding void. In 2014, astronomer Brent Tully and colleagues published a paper that redefined our understanding of our cosmic home. Rather than defining superclusters arbitrarily by their apparent concentration in space, Tully's team mapped the actual flow of galaxies, the direction of gravitational motion across a vast region of the universe. By finding the boundaries within which all galaxy motion was directed toward a single gravitational basin, they defined what they called Laniakea, the supercluster we live in. Laniakea is approximately 520 million light-years across. It contains the mass of approximately 100 million billion suns, distributed across roughly 100,000 galaxies. The Milky Way is one of them, located, it turns out, on the outer edge of Laniakea, toward its periphery. At the center of Laniakea's gravitational basin, the point everything inside it is slowly falling toward is a concentration of mass known as the Great Attractor. It sits roughly 250 million light-years away, in the direction of the constellations Centaurus and Norma. It cannot be directly observed in visible light because it lies behind the zone of avoidance, the plane of the Milky Way itself, where our galaxy's own dust and gas blocks our view of whatever lies behind. We know the Great Attractor is there because of its effect. The Milky Way is moving toward it at approximately 1,400,000 miles per hour. thousands of other galaxies are also moving toward it. Everything in Laniakea is slowly, inexorably, falling in its direction. The Great Attractor is not a single object. It is a broad concentration of mass associated primarily with the Norma cluster and the surrounding overdense region. It is a node, a knot, in something larger. Laniakea, with its 520 million light-years of extent, is not the end of the hierarchy. Beyond Laniakea, and exerting gravitational influence on it, sits the Shapley Supercluster, the most massive concentration of matter in the nearby universe. Located approximately 650 million light-years away, the Shapley Supercluster is roughly 10 times as massive as Laniakea. It contains the mass of tens of millions of billions of suns, some of the most extreme galaxy concentrations known. Its gravitational pull is significant enough to affect the motion of galaxies hundreds of millions of light-years away, including, indirectly, our own galaxy. We are falling toward the Great Attractor. The Great Attractor is falling, along with the rest of Laniakea, toward the Shapley Supercluster. Everything is in motion. Everything is falling towards something larger. But even the Shapley Supercluster is, at the scale of what comes next, a single bright point at the intersection of two threads in a web. At a large enough scale, the universe reveals something nobody who first glimpsed it was entirely prepared for. Structure, not the gentle clumping of matter that theorists had broadly expected, not a vaguely random scattering of galaxy clusters, here a little denser, there a little thinner, something organized. Something geometric, a three-dimensional network of dense filaments and sheets interconnected at bright nodes, enclosing vast, dark bubbles of near emptiness. Something that looks, unmistakably, like a web. The first hints appeared in the 1970s and 80s as astronomers began systematically mapping galaxy positions across large swaths of the sky. A survey of galaxies in the region of the Coma supercluster revealed that the galaxies were not spread through space evenly. They were concentrated into a thin sheet, a pancake of galaxies with enormous empty regions on either side. Further surveys revealed more sheets, more filaments, more voids. By the time the first digital sky surveys began producing maps of tens of thousands of galaxies in the 1980s and 90s, the picture was unmistakable. The universe is not smooth. It is a sponge, a foam, a web. We call it the cosmic web. The cosmic web is the largest structure in the observable universe. It is not one thing. It is the pattern, the shape that all matter has been organized into over the full history of cosmic time. Filaments of dark matter and gas, hundreds of millions of light-years long, connecting dense clusters at their intersections and enclosing vast voids between them. Ordinary matter, the gas that becomes galaxies, that becomes stars, that becomes planets, that becomes everything you can see or touch, traces the dark matter scaffolding the way a river traces a valley. The dark matter was there first. The ordinary matter followed. In 2021, astronomers published the first direct detection of an individual cosmic filament connecting two galaxy clusters. The filament was approximately 10 million light-years long, roughly the diameter of the entire local group, consisting of gas at temperatures of 10 million degrees. So diffuse, it had been almost impossible to detect. It had been predicted by cosmological simulations for decades. Seeing it confirmed that the web exists not merely as an artifact of our mapping methods, but as a real physical structure in space. In 2023, observations with the Very Large Telescope found evidence of gas filaments rotating entire cosmic filaments, hundreds of millions of light-years long, spinning on their own axes. The implications of this are still being worked through. It suggests that angular momentum, the tendency of matter to spin, operates not just on the scale of planets and stars and galaxies, but on the scale of the largest structures that exist. There is something strange and beautiful in this discovery. The same principle that makes a figure skater spin faster when they pull in their arms, conservation of angular momentum, may operate across structures hundreds of millions of light years in extent. The universe spins at every scale we have examined. Apparently, it does not stop. The cosmic web is alive in ways we are only beginning to understand. At the nodes of the cosmic web, the bright intersections where filaments meet, sit the most massive galaxy clusters. Material has been flowing toward these intersections for billions of years, funneled along the dark matter filaments like water running down creases in a folded sheet. The clusters at the nodes are the endpoints of enormous cosmic rivers of matter, the gravity drains of the universe, the places where everything eventually falls. Between the nodes and along the filaments, galaxies move, not randomly, but in coherent flows, rivers of galaxies streaming along the filaments, group by group, cluster by cluster, all flowing toward the massive concentrations at the intersections. This is not a small-scale phenomenon. These flows operate across hundreds of millions of light years. Mapping them has been one of the great achievements of observational cosmology in the last few decades, revealing the skeleton of the web not just through where galaxies are, but through how they are moving. Within the cosmic web, astronomers have catalogued structures of extreme scale so large that some of them strain against the theoretical limits of what should be able to exist in a universe governed by standard cosmological models. The Sloan Great Wall was discovered in 2003 using galaxy positions from the Sloan Digital Sky Survey. A vast sheet of galaxy clusters and filaments, approximately 1.4 billion light-years long, curving through space about 1 billion light-years from Earth. At the time of its discovery, it was the largest known structure in the observable universe. The South Pole Wall, identified in 2020 by a team using infrared surveys that could partially see through the zone of avoidance, is a massive concentration of galaxy clusters stretching approximately 1.4 billion light-years, largely hidden behind our own galaxy. The giant arc, announced in 2021 by Alexia Lopez at the University of Central Lancashire, is a curved structure, approximately 3.3 billion light-years long, found in the distribution of quasars and distant absorbing gas clouds at a redshift of about 0.8, roughly 9 billion light-years away. The giant arc is particularly interesting not just for its size, but because its existence is difficult to explain under standard cosmological assumptions. The principle that the universe should appear statistically uniform at scales above roughly 1.2 billion light-years, called the cosmological principle, predicts that structures larger than about 1.2 billion light-years should not exist. The giant arc is nearly 3 times that size. And then there is the Hercules Corona Borealis Great Wall. First reported in 2013 and subsequently revised by several groups, the Hercules Corona Borealis Great Wall is estimated at approximately 10 billion light-years across detected, not through the distribution of visible galaxies, but through the clustering of gamma-ray bursts, the most energetic explosions in the universe, which can be detected across nearly the entire observable universe, 10 billion light-years. The observable universe is 93 billion light-years in diameter. If the Hercules Corona Borealis Great Wall is a real gravitationally associated structure rather than a statistical artifact of how gamma-ray bursts are distributed, it is a single coherent structure spanning roughly 1/10 of Rayleigh and 1/10 of Mest. everything we can see, whether it represents a genuine challenge to the cosmological principle or whether it will dissolve under more careful analysis, is still being debated. But its very existence as a candidate, the fact that we keep finding things at larger and larger scales than our models predict, suggests that our understanding of the large-scale structure of the universe may still have surprises waiting. Between the filaments and walls of the cosmic web sit the voids. Voids are the dark complement to the web's bright structure, vast regions where matter is sparse, where galaxy density is far below the cosmic average, where the web is thin or absent and the darkness is deep. They are not empty. Even inside a void, there are scattered galaxies, but they are lonely places. The Boötes void is one of the largest known supervoids in the observable universe. Located approximately 700 million light-years away, centered on the constellation Boötes, it spans approximately 330 million light-years. Inside the Boötes void, surveys have found approximately 60 known galaxies. In a region of equivalent volume in a typical part of the universe, you would expect to find around 2,000. The Boötes void is so empty that when Robert Kirshner and colleagues discovered it in 1981, they initially thought they had made an error. Structures that empty, that large, were not predicted. Kirshner described it, famously, by noting that if the Milky Way sat at the center of the Boötes void, we would not have discovered the existence of other galaxies until the 1980s, because there would have been no nearby galaxies to observe. The void is so vast that even with the optical telescopes available in the mid-20th century, there would have been nothing to see in any direction for hundreds of millions of light-years. We may ourselves live inside an underdense region. The KBC void, identified in 2013 by Keenan, Barger, and Cowie, is a local underdensity approximately 2 billion light-years across, with the Milky Way near its center. The entire local group, the entire Laniakea supercluster, sits inside a region of space that contains measurably less matter than the cosmic average. This may explain one of the most persistent puzzles in modern cosmology, the Hubble tension. Measurements of how fast the universe is expanding give two different answers depending on how you measure it. Local measurements using standard candles like Type 1a supernovae and Cepheid variable stars give a higher value than measurements derived from the cosmic microwave background. The difference is small in absolute terms, but large enough statistically to be difficult to dismiss as measurement error. One candidate explanation is the KBC void. If we live inside a large underdensity, the matter immediately around us is less dense than the cosmic average. There is less gravitational drag on the matter around us. Local expansion would be slightly faster than the global average. Local measurements would be biased high. We would be systematically mismeasuring the expansion rate of the universe because we happen to live in a hole. There is a certain humbling quality to this possibility. We have spent decades debating the precise value of the Hubble constant, running increasingly careful experiments, refining our standard candles, improving our measurements of the cosmic microwave background. And the answer to the discrepancy may simply be that we are not in a typical part of the universe. We are in a void. Our measurements are locally correct. They are globally misleading. The universe, it turns out, is not obligated to arrange itself so that wherever we happen to find ourselves is a representative sample. We do not live at the center of the universe. We may live in a hole in it. The cosmic web was not designed. It was not planned. It was not set up in advance by any process that had a goal or an intention. It emerged. In the first tiny fraction of a second after the Big Bang, before the universe was even 1 second old, quantum fluctuations generated random tiny variations in the density of matter across space. These fluctuations were stretched to cosmological scale by inflation, the period of exponential expansion that may have preceded the hot Big Bang itself. Across the entire observable universe, the density varied by roughly 1 part in 100,000, the temperature variations we see today in the cosmic microwave background. 1 part in 100,000. From that near-perfect uniformity, gravity began to work. Dense regions pulled in more matter. Less dense regions lost matter to their neighbors. Over millions of years, then hundreds of millions, then billions, the small became significant. Dense filaments of dark matter formed first, because dark matter is free of the pressure that ordinary matter experiences. Ordinary matter hydrogen and helium gas flowed along the dark matter filaments, concentrated at their intersections, and eventually, in the densest regions, began forming stars and galaxies. Consider the chain of contingency in this. A quantum fluctuation, a random variation in the vacuum of the very early universe, tinier than any scale we can directly probe, was stretched to the size of a supercluster. Gravity spent billions of years amplifying it. The result is a filament hundreds of millions of light-years long, containing billions of galaxies. Trace any thread of the cosmic web back to its origin, and you arrive at randomness, at a quantum event in the first fractions of a second of the universe's existence. The web is, in this sense, a memory. It is the universe's record of its own earliest moments, written in the largest possible handwriting, across the largest possible surface, 13.8 billion years of gravitational amplification of a 1 in 100,000 density variation. That is what the cosmic web is. The universe built its largest structure from a whisper, and inside that structure, in one filament, in one supercluster, in one galaxy cluster, in one small group, in one galaxy, in one spiral arm, in one planetary system, on one rocky world, something happened that the universe has apparently not arranged very often. Something became aware. Something started asking questions. Something looked up. The observable universe is approximately 93 billion light-years in diameter. That is not the size of the universe. That is the size of the portion we can observe the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang. The universe itself, if current theories are correct, extends vastly further. Inflationary cosmology suggests the true extent of space may be somewhere between 10 to the 23rd and 10 to the 100 times larger than the observable portion. These are not numbers. They are gestures toward a scale that has no analogy, no comparison, no reference point anywhere in human experience. Beyond the boundary of the observable universe, events are occurring right now. Light is being emitted. Stars are burning. Galaxies, presumably, continue to arrange themselves into the same cosmic web pattern that we see around us. None of that light will ever reach us. The regions beyond our horizon are receding from us faster than light can travel across the expanding space between us and them. No signal can bridge that gap. No message could ever arrive. Whatever is out there beyond the edge of what we can see is, in every physical and practical sense, not part of our universe. We are sealed inside our observable bubble, not by walls, not by force fields, by physics, by the finite speed of light and the finite age of the universe and the accelerating expansion of space that will, in the far future, progressively cut us off from even the galaxies we can currently see. The galaxies we can see today will, over the next hundreds of billions of years, gradually recede beyond our horizon. One by one, the lights will go out not because they have died, but because the space between us and them is expanding faster than their light can cross it. Eventually, in a universe vastly older than ours, all that will remain visible to any civilization that might still exist in the Milky Way will be the local group Andromeda, already merged with us, and a handful of dwarf companions adrift in an otherwise apparently empty universe. Future astronomers, if they exist, will look out into space and see nothing but darkness and conclude that the universe is small and lonely and unchanging. They will have no way of knowing that their sky was once full of light. The evidence will have receded beyond all possibility of detection. They will have no cosmic web to map, no distant galaxies to study, no hint that the universe once contained structures of extraordinary complexity and scale. They will be epistemically imprisoned by the universe's expansion in a way that we, in our current era, are not. We live in a privileged moment. The universe is young enough that the web is visible, old enough that we evolved to look at it. You have now traveled, in whatever way, a journey through language and numbers and imagination can constitute travel, from Earth to the edge of everything. From a rocky planet 7,900 miles across to filaments of dark matter 10 billion light-years long. From a familiar place with a name and a view and weather and seasons to a web so large that the word large has worn smooth from use and means nothing anymore. The cosmic web does not know you made this journey. It does not know you exist. The universe has no capacity for knowing anything, no mind, no preference, no awareness of its own structure or its own history. It does not experience the grandeur of what it has assembled. It does not feel the beauty of the filaments it has woven, or the depth of the voids it has carved. It does not know that something on one small planet, in one minor arm of one ordinary galaxy, looked outward and tried, imperfectly but sincerely, to understand what it was looking at. That knowing is entirely yours.